Come on in, everyone. Anyone have any questions before we get started? Hope you had a good weekend. Got your test done. And of course, ready for your next test, which is due Wednesday. Anybody have any questions before we get all started? Jacqueline is trying to get in. We only got 9 people in here right now. Let's see. So the test wasn't on the actual Canvas page. I only found it on my dashboard. Were you able to take it, Jared? Okay. That's weird. I don't know why it wasn't on your Canvas page. Let me double check something real quick. That's weird. Because I need to make sure the other one's not like that. Oh, great. Let's see. My system resources are low again. Ugh. I see test 3 listed in online test. I see test 4 listed. No, I see test 5 listed in online tests. I don't know why it's not there. So
I had found it in the grades thing. Like if you go to grades and then you can find it, it's in some folder called nothing. So it wasn't in with the rest of the tests for some reason.
That's weird. I'm glad y'all know your way around Canvas better than I do, because I don't think I could have found it. I guess, okay, if you were one of those cases that couldn't find it, I'm going to allow you another day to take it. Did anybody not get a chance to take it? Whether it's that you didn't get a chance to take it or you just couldn't find it, either way, you're getting another day, because it's truly not unfair, not very fair of me to do it that way. So I apologize. I now have it available on the online test thing, and I don't know why it ended up where it was. That's weird. I could have sworn I went through and did that. But anyways, let me change it to right now while we're talking. I'm going to change the due date to, and since I'm being generous here and realizing that I screwed up, I'm going to change the due date not to tonight. I'm going to change the due date to, but they'll both be due on the 17th. So the due date and the last date of appearance for that test is now the 17th at 11:59 p.m. So sorry about that, folks. And no one will get any penalties. I had one student that missed it in my morning class, but he didn't say for that reason. He just said he completely forgot it. I'm going to check and see if I did the same thing to them. I might have to give him credit for that as well. Anything else anyone have? All right, well, we've taken care of that. That's good to hear. Thank y'all for that, and I apologize for the inconvenience. Remember, you now have 2 tests due on Wednesday the 17th, so make sure you get those done. I can see test 5. Hopefully y'all can too. Anything else? Luckily, I'm not tired, so I'm not going to be yawning or anything. Thanks, Jared. All right, well, let's get started on this. So we were talking last time about several things, but one of the things I tried to reiterate to you was the importance of the harmonic oscillator, specifically mass on a spring, and why we study it so much. And I gave you heuristic arguments about why that was so important and how it appears everywhere. And really, at the end of the day, if you have a differential equation or any kind of equation that defines something, and then you see that same equation in other things, then you always know the laws that you learned from that equation are applicable to all those other things. So in doing so, I also suggested you do the Mclaren Series. So I'm going to give you the actual answers to that Mclaren Series and ask you guys to do it for extra credit homework. But remember, when you expand a function in terms of a Mclaren Series, which is different than a Taylor Series, the Taylor Series is more general. You just say, what can I approximate f of x as when x is equal to a? And that's the Taylor Series. But when you do the same thing for when x is equal to 0, that's called the Mclaren series. And basically, if it meets certain criteria, which I said is almost always the case for physical solutions, then the summation from I equals 0 to infinity of 1 over I factorial, the ith derivative of the function evaluated at x equals 0 times x to the ith power is the Taylor series is the Mclaren series expansion. Now that we have that, I want to tell you what sine is and cosine is and all that good stuff. So there's a couple of neat little things that come out of this, and all of these combine when you see f of x equals sine x, f of x equals cosine x, and f of x equals e to the x. You'll see how easy it is to remember these. So it turns out that f of x equals sine x is basically you start off with x, and that's technically 1 over 1 factorial times x to the 1 power. The next term is minus, and it's another odd function. So this is x to the 1 power. This will be x to the 3rd power. So it's going to be 1 over 3 factorial x cubed. Then it'll be a plus, again, another odd one. So it's 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus 1 over 9 factorial x to the 9 minus ... I think you probably could have seen the pattern even with just those terms, but I gave you quite a few there, so hopefully that's helpful. Poor Jacqueline's having a hard time getting in. Now, some things that can remind you of that. Remember, the sine function looks like this. Goes up, down, back like this. But then the reflection of it about the y-axis is exactly the opposite. So this is what's called an odd function. And this is why they call it odd. You can see these are just odd terms that make it up, right? So that's why the sine, or another test of the sine of whether it's odd or even, is what is the sine of negative x. In this case, it's the negative of the sine of x, and that makes it an odd function. And it's always going to have an inverted mirror image along the y-axis. The cosine, on the other hand, is an even function. And you'll see with that one, we get f of x equals cosine x is going to be 1. And that's actually technically x to the 0 power times 1 over 0 factorial, but 0 factorial is defined to be 1. And then just like this one, it's going to have pluses and minuses and all that good stuff. So it'll be 1 minus, we have to skip the 1 power because that's actually an odd function. So it's 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th minus 1 over 10 factorial x to the 9th, or excuse me, x to the 10th, plus ... So you can see, well, we'll talk about this a little bit later about what the value of this is, but you can see these are all even powers, and that also helps you understand it being an even function, because in this case, cosine looks like this, and its mirror image is identical. So that's the even function, and not only that, that's decided to be so because cosine of negative x is equal to the positive cosine of x. So you can see the differences there. Now, this all might seem a little bit weird and all that good stuff, but it really is pretty straightforward, especially once you actually take the time and see what e to the x is. So with e to the x, we say f of x is equal to e to the x. And lo and behold, that is 1, which is really 1 over 0 factorial x to the 0 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th. You see that if you got rid of all the negatives and just added these two, they would clearly be the same thing. And because of that, you can see if you try to take and plug in for e to the x, say f of theta is going to be e to the I theta. If you do that, you can see that when you put in I theta here, for instance, you're just going to get I times theta. When you put it here, you're going to get negative 1 over 2 factorial x squared, which is that. And when you put it here, it's going to get negative I times 1 over 3 factorial x squared, which is just I times this one, and so on and so forth. So you should be able to see that this gives us cosine theta plus I sine theta, which is Euler's formula. Okay, so you can do this, show at least, I think I'm going to go with 9 non-zero terms. For each for extra credit. Okay, so you can do all that for extra credit, and it comes in handy because we're going to make use of it today. But it's also something that is used so often in physics and engineering that it's really our science in general and engineering. It really is worthwhile to have. I suggested you also do parenthesis 1 plus x close parenthesis to the n power, and that's a useful one as well. But these three are really, really important, and you should take the time to do it. You're going to see that really there's 4 terms. When you take the 0th derivative of sine, the 1st derivative of sine, the 2nd derivative of sine, and the 3rd derivative of sine, that's 4 terms. The 5th one, it starts repeating itself. Same thing with cosine, same thing with e to the x. Actually, e to the x is even sooner. So it's really not nearly as daunting as it sounds. You can see the pattern within, like I said, 4 moves. All right. So now that we've done that, now that I mentioned all that, because I'm going to make use of this top one today. But the first thing we want to study is, in fact, something called the simple pendulum. And there's a couple ways you can solve the simple pendulum. I like to use the torque equation. So that's what I'll use. So let's start off with the simple pendulum. And then I'll give you a nice example of it. And simple pendulum, Pendulum. So what we have is a ceiling to which is fixed a rope or string of some sort. Okay, we're not examining the case where the string gets taut or shook or anything like that. We're just imagining it has a mass hanging on it. We pull it taut, lift it back, let it go. And what we find out is, in fact, we're going to release it at some angle theta. And we're going to use the Newton's second law version for torque is equal to I times d2 theta over dt squared. We're going to use that to solve the problem. So here's the mass, mg. Well, there's the mass, and then of course the mg is the vector hanging off of it. I don't know why I wrote mg there already, but mg of course points vertically downward, so that's mg. But you can see you can break up this weight into 2 terms that are perpendicular to each other. This one's going to be mg cosine theta, but that's parallel to the lever arm, and this one's going to be mg sine theta, and that one's perpendicular to the lever arm. So we've already seen that torque is r perpendicular times f, but it's also f perpendicular times r. So we're going to use that version, and we're going to say the pendulum has a length L. So the moment of inertia for a point particle on a circular orbit at some radius L is just ml squared. So we know I now. We can figure out torque. That's just going to be this component times the lever arm, which is L. So we can now write it like this. Now remember also that as theta gets larger, or theta going that way is resulting in the force going this way. So those two actually have to be oppositely directed, and therefore there's a negative in it. So I'll get negative mg sine theta, there's the force, times the lever arm L, there's the torque, and that's going to be equal to m L squared d2 theta over dt squared, because like I said, for a point particle going in a circular orbit of radius L, the moment of inertia is just ml squared. With this one, we can now divide through both sides by 1 over ml squared and put both all the terms on one side of the equation. And when we do that, we'll get d2 theta over dt squared. Notice the ml squared leaves nothing in front of it. And now I'm going to get plus the ml squared down here in the bottom is going to take out one of those L's, and it's going to take out the m, but it's going to get g over L times the sine of theta equals 0. Now that is decidedly not a harmonic oscillator equation. In fact, this requires what's called an elliptical integral to solve. Remember, the harmonic oscillator equation was d2x over dt squared. So this top variable, notice that's x. This other variable, the argument of the function is t. We had that equal to k over m, some constant in other words, times x. So notice this matches what the derivative is being taken of, okay? And from that, we were able to say that x is equal to a cosine omega t plus phi. So whenever we get a second order derivative of something, and then that something times a constant equals 0, then we know this is a solution, and we know that omega is equal to the square root of whatever that constant was. In this case, it's k over m. Okay, and of course that's 2 pi f. So we can get an f out of it, and period, of course, is 1 over f, so we can get a period out of it. So all those things are fair play, but right now we don't have that form. But if we assume theta is close to 0, and believe it or not, when theta is as small as 15 degrees, sine of theta in radians is only about 1% different from theta in radians. So it's really pretty good. So if we assume that, we can look at our sine function, and when theta equals, let's say something really, really small, let's say 0.1. So that means this would be 0.1. And then this term would be 0.1 times 0.1 times 0.1. That's 1/1000th. And then this would be 1 over 6, because 3 times 2 times 1 is 6. So this would be literally 1 over 6,000, which is way, way smaller than the 0.1. So from that, you can already see that, oh, okay, well, this is obviously a negligent term or a negligible term. So in this case, we can say sine theta is approximately equal to theta. Now we get something we can work with. d2 theta over dt squared plus g over L times theta is equal to 0. And that is exactly the same form. Second derivative with respect to time of something. In that case, it was x, and x appeared here. In this case, it's theta, and theta appeared here. There's a there's a constant in front of this. Well, there's a constant in front of this. It just happens to be g over L. So now we can automatically say that theta is equal to, you could actually go ahead and realize what it is. It's theta max times cosine omega t plus phi. And of course, that means omega is going to be equal to the square root of g over L, because that's the constant there. And of course, that means f is going to be omega over 2 pi. So that's 1 over 2 pi times the square root of g over L. And then t is going to be 1 over f. So you can see that's 2 pi times the square root of L over g. So all of these are new facts that we can make use of when we're solving a pendulum problem. We don't have to go back and solve the differential equation. We just use these. And in fact, anytime you see a differential equation like this, you can use these. So let's attack an example. Let's say example 1. Some geologist. Now I'm going to make this a little bit shorter. Some geologists will actually go out and measure G very precisely because that can tell them things about the local part of the Earth. In other words, wherever that at on the surface of the Earth. For instance, let's imagine that you had a big bubble of uranium right below the surface where you're standing. That uranium is so dense compared to dirt and stuff that's all around it. You might actually expect the gravitational acceleration to be quite a bit higher there because of the increased mass. So they can use that value of G to determine some of the things that might be actually under them. So if they have a very precise way of measuring the period of a pendulum, then they can use that to determine things about it. So I'm going to say some geologists found that at a particular location, a pendulum, simple pendulum, with L equal to 26.43 centimeters had, whoa, I just made an H into an F, had a frequency F equals 0.9705 hertz. So I'd like to know what is G there. So that's the big question. Now, I'm not sure whether modern geologists still use pendulums. They might have some other techniques they can use as well that are even easier to deal with, because you can imagine the difficulties with the pendulum, because you know, if you have air resistance and stuff like that, you also have to have it, you know, make sure it's kind of level, make sure there's no air circulating in and out of it, stuff like that. So there could be some different problems. Plus, you got to make sure the mass is much larger than the mass of the spring, or excuse me, the mass of the string, string. So there's some things wrong with that, but it, you know, it would definitely serve you if you're interested in geology to ask around and see whether that's what they're doing. I haven't been to the campus in so long. I haven't been able to talk to my geology friends about this, but anyways, here we go. What is G there? Well, what we do know is that this right here, all these have G in it. And what they gave us was the F and the L. So, hey, I've got an F, I got a G, I got an L. So I'm going to use that. And what I'm going to say is F is equal to 1 over 2 pi times the square root G over L. So I can take 2 pi F instead of equal to the square root of G over L, because that's really what omega is anyways. And then I can square both sides, and I get 4 pi squared F squared is equal to G over L. Or finally, you find that G is equal to 4, or let's do it a little more succinctly. Let's go ahead and write 2 pi F and put all that in parentheses and square it, and then write it times L. Well, that's going to be 2 times pi times F, which is 0.9705 hertz. Now, let's not forget what omega equals 2 pi F is doing. Omega equals 2 pi F is really converting cycles to 2 pi radians. So you can sort of pretend this 2 pi is radians per cycle, and then this hertz really is cycles per second. So you can see what's happening there. Then you're going to square that, of course, that whole thing. And then you're going to multiply it by L, which needs to be in meters, so you can get 0.2. Whoa. I put an extra 0 in there. That's what happens when you're talking while you're writing. Your brain just writes down whatever you say. So 2.643 meters. Now you can see this is radians squared per second squared, but radians just meters per meter, so it's not really a unit. And this is meters, so I got meters per second per second. That's exactly the unit you want. Y'all should verify this calculation. I did it earlier, so I can write it down. It's 9.8276 meters per second, and I carried one extra sig fig. Remember, if you're just talking quick calculations with the numbers you know, you can use sig fig rules. Really, if you're trying to report an experimental result, you really should be using propagation of error formulas. But I just indicated this by showing one extra sig fig, and you should see basically by 4 sig figs and 4 sig figs, everything's being multiplied. You should get 4 sig figs. That's why 9.828 should be the answer. Any questions on that? Okay, so I think that's a pretty straightforward application of the harmonic oscillator differential equation. But as you can tell, it was a little more complicated because it came out with that nasty sign. And like I said, that would really require elliptic integrals. So that's something you can look up if you're into math. So we actually do know how to solve this in all its glory. But to be honest with you, in our labs, we do this and we'll do several different lengths all the way up to like 1.2 meters for the length of the pendulum. And we'll do several different angles. We'll go literally up to 60 degrees. And when you calculate the period using this formula, and you compare that to the period you find when you use 60 degrees, you're only off by like 2%. So it really is sine theta approximately equal to theta is pretty good to a pretty high range, at least regarding the period of the motion here. So no questions about that? All right, well, what I'm going to do next is consider something a little more complex, and that's going to be a physical pendulum. Okay, so right here I'll say physical pendulum. Okay, now with a physical pendulum, what you have is sort of a blob of mass of any kind of random shape, if you will. Let's say this is the point about which you're rotating it. And let's say the center of mass is right here because it's not uniformly distributed. So there's my CM right there. So this line right here might have a length h from the point of rotation to the center of mass. And in fact, this angle right here might just be theta again. Okay. And let's say this thing also has a mass m and has a moment of inertia about this particular point, I. Okay. So again, we have the summation of the torques is equal to I times d2 theta over dt squared. So in this case, we're going to have, this is going to behave just like the mass, m, is acting right at the center of mass. That's sort of the definition of the center of mass. And of course, that's going to be mg pointing straight down. And again, we'll have an mg sine theta as the restorative force. It's a force that as theta gets big, it's going to try to turn it back to theta being small. So again, we're going to get negative mg, but this time instead of L, we're going to get h sine theta is in fact equal to I d2 theta over dt squared. So if I divide both sides by I and put them all the terms on one side, then I'll get d2 theta over dt squared plus mgh over I times the sine of theta is equal to 0. Again, using the small angle approximation, That's what that's called. We get d2 theta over dt squared plus mgh over I theta is equal to 0. So guess what? We've got a whole nother scenario where we know neat stuff. And the new scenario where we know neat stuff is that theta is equal to theta max times cosine omega t plus phi. And omega, which is also 2 pi times f, is going to be the square root of mgh over I. And f is therefore going to be omega over 2 pi, and t is going to be 1 over f. So I'd say that's 2 pi times the square root of I over mgh. So now, all because of this and the similarities with that differential equation, we've got all new functions which are surprisingly similar that can be used for a physical or compound, well, I'll say physical pendulum, which basically just means a pendulum that's not a string that's infinitely light and a mass that's infinitely heavy, so that the two don't, intermingle or anything like that. So that's a physical pendulum, despite me calling it a pendulum. So any questions on that? All right, so that's sort of what's happening in physics, is you're slowly just learning all these different scenarios in which certain equations you've already studied apply. So now let's actually use this finding to solve a problem. Okay, so we just solved the physical pendulum problem, and what I want to do is do example 2, which I'll write in black since I did that last one in blue. So this will be example 2, or I did that last paragraph. So in this case, I'm going to say a cylinder, I'm assuming it's a uniform cylinder, of course, of mass m and radius r is hanging and oscillating as shown. What are omega, f, and t? Okay, so here's how I'm going to say it's shown. So let's imagine this is our cylinder. Okay, you could actually maybe make out a little bit of the fact that it has some thickness to it right here, say. But what it has is right here is the center of mass. And right here, from here to here, is 7/8 R. And of course, this is R, and this is mass M. Okay. And what I'm saying is this is the angle that we've actually stretched the object out to. Okay. So that being the case, I can now solve this. The solution just requires us to realize that this is a cylinder, and this moment of inertia for a cylinder about the center of mass of the cylinder is just 1/2 mr squared, which I derived for you guys. And we also have the parallel axis theorem. which I'll abbreviate FUM. Okay, so that tells us the I for this cylinder is going to be 1/2 mr squared. That's big M. Sorry about that. 1/2 big M r squared plus big M times the distance away from the center of mass that the actual pivot point is. So in this case, I'm going to have to say 7/8 r, and then that quantity squared. So I get 1/2 mr squared plus 49/64 mr squared. This is 32 64 plus 49, so that'd be 81/64 mr squared is the total center of mass of the cylinder. Everybody follow what I did there? Now, we just finished learning, you can check back in your notes, of course, but we just finished learning that for a physical pendulum, omega is equal to the square root of mgh over I. So now I have I, and I know what h is, so I can immediately write that omega is equal to the square root of m times g times 7/8 r, because that's what h is, divided by 81/64 mr squared. Now you can see some stuff happening. That m is going to cancel out with that m. This r is going to cancel out with one of those exponents. And of course, 81/64 in the bottom becomes 64/81 in the top. And of course, 64 is a perfect square and 81 is a perfect square. So we can actually figure out the perfect square of this. 8 times 8 is 64, 9 times 9 is 81. So I'm going to say, when this comes up top, I'm going to get 8 over 9 times the square root of 7 g over r times 8. Of course, you can also realize that this 8 is 2 root 2. So you could say 8 over 2 times 9 times the square root of 7g over 2r. And of course, this will cancel out with that. And finally, I get omega is equal to this 2 canceling out with that would be 4. So I'm going to say 4/9 square root 7g over 2r. And that's my omega. Now I can also calculate my F by F is equal to omega over 2 pi. And when I do that, I just get, notice the 1 over 2 pi down here. The 2 is going to cancel out with the 4. So I can just say 2 over 9 pi times the square root of 7g over 2r. So that's my frequency. It's a little better when I write the box with a slightly different color. I think it stands out a little better. Okay, and of course the period is just 1 over that. So the period is going to be 9 pi over 2 times the square root of 2r over 7g. Now notice I didn't analyze the units before. I was waiting until I got here, specifically because it's a little easier, and as long as we didn't make any mistakes to get here, if this comes out right, it's highly likely that there were no mistakes beforehand. But notice this is R has units of meters, gravitational acceleration has units of meters per second squared. So this meters per second squared in the bottom becomes second squared per meter in the top. And then meter here and meter in the bottom just gives you square root of second squared, which is exactly what you expect. Someone have a question? I thought I heard a murmur of some sort. Okay. So see how just knowing these fundamental equations, you can get so much information, so much helpful stuff out of it. So what I thought I'd do next is now that we've covered the physical pendulum, the simple pendulum, all we've got is the damped harmonic oscillator and the forced harmonic oscillator. As far as the force goes, I'll let you see my YouTube video on that because you're only going to be required to, apply the formula very straightforwardly like the book does, and maybe one problem in homework. I'm not going to test you on the forced harmonic oscillator on the actual test, but you are responsible for playing with it as far as far as homework goes. So let's do the damped harmonic oscillator. So damped harmonic oscillator. Okay, with a damped harmonic oscillator, your book does it one way, which I don't care that much for it. I mean, it works, but the derivatives and stuff involved are really nasty, because what your book does is it says x of t as like an ansatz guess, remember? X of t, he says, well, I suspect it's going to be like cosine with an amplitude in front of it, but I'm also going to put a e to the negative gamma t out there and then call this cosine omega prime t plus phi. And that actually works. Notice you'll have to actually do the differential equation, you're going to take the second derivative, the first derivative, all that good stuff. But taking a derivative, and in fact a second derivative of a function times a function, leads to a lot of crap. So that's what I don't like about it. So let me go ahead and write out Newton's second law for the damped harmonic oscillator. So for the damped harmonic oscillator, what you have is say a mass on a spring like this, but there's just a spring with no mass. But then once you bring in the actual mass, the spring stretches and you get a mass m right here. Okay, now notice the force that the string applies, F, is of course pointing that way. So it's negative k times x, because again, if this was your x-axis, this positive x pointing down would suggest the force is pointing up because of this negative, and that's exactly what you expect. But in addition to that, we are also going to have a resistive force that's directly proportional to the velocity, and that's the air resistance. So we'll say F is negative B times V. So that's another force we're going to be dealing with. So what I'll have is the summation of the forces is equal to m. Again, the masses aren't changing, so we can use our old school version of Newton's second law, which is ma instead of dp dt. So when I do that, I'm going to get this. I'll say negative b dx dt, because velocity is the derivative of x with respect to time, minus kx is equal to m d2x over dt squared. Now I'm going to divide both sides by 1 over m and put all the terms on one side, and I'll get d2x over dt squared. Once this comes over here, it'll be plus b over m times dx over dt, and plus k over m times x, and all that's equal to 0. Okay, so this is the damped harmonic oscillator equation. And you can see the difference is instead of just having a second order derivative and a zeroth order derivative, we actually got a second, first, and a zeroth. And there's constants in front of them. So whenever you have that scenario where this, and this match, and there's a constant and there's a constant, or if there's even a constant there because you can divide through by that constant, then you know this solution that we're going to work out is the right one. So here's what we do. I'm going to do it the way that you normally do it, say, in a differential equations class, as opposed to the way you do it like Mr. Giancoli is. And it's really not any different. We're just going to, well, we're going to make a realization, okay? So what I'm going to do is I am going to say that let's let x equal some constant times e to the rho t. Now, this might seem weird. It doesn't have a sine or a cosine in it, but trust me, a sine and cosine will come. But it's not, it's going to, by doing this way, it's not going to obscure the fact when there aren't cosines there. And that's what I think a lot of people missed when they're dealing with harmonic oscillator. I know I did when I covered it. So now I can say dx dt, the first derivative of x with respect to time, is just a rho e to the rho t. And I can say the second derivative of x with respect to time squared is a rho squared e to the rho t. So now I can plug all this junk in. I'm going to get a rho squared e to the rho t for that first one, plus b over m a rho e to the rho t, plus k over m times a e to the rho t equals 0. Now I have a common factor of a e to the rho t, so I'm going to factor that out. What I have left is a rho squared plus b over m rho plus k over m times a e to the rho t is equal to 0. Since this is Newton's second law, it is true for all time. Okay, and the only way that can be the case is when rho squared plus b over m rho plus k over m is equal to 0. Okay, that's the only way this can be true, because obviously various rhos are going to give you different values, and there might be a rho, and in fact you can't tell it, but there shouldn't be a t such that the e to the rho t gives you 0. Even if you put 0 up there, you're still going to get 1. So in fact, the only way you can force this to be 0 is by all of this being 0. And then we just get to use the Pythagorean theorem. And the Pythagorean theorem says that rho is equal to negative b, which would be negative b over m, plus or minus the square root of b squared. That's this again. So that's b over m quantity squared minus 4 times a, which is 1, times c, which is k over m, all that over 2a, which is again 1. Okay, now I'm going to take this 2 and distribute it amongst these two fractions, and I'm going to get negative b over 2m plus or minus. Now I'm going to pull that 2 inside the square root, so that's going to become 2 squared inside the square root, because that's the only way you could get it out and have it be 2. So this is going to be b over 2m squared minus the 4 is going to cancel out with the 2 squared on the bottom, so it's going to be k over m over here. So that's what rho is. And it turns out, since this is a second order differential equation, you actually have to have 2 solutions. Just like with a second order algebraic equation, you have to have 2 solutions. So if we had the weird case of b over 2m squared being equal to k over m, then this disappears and there's a whole different set of rules that you go by. But all the terms are going to have this. So I'm going to handle each of those cases initially. So I'm going to first start off with B over 2m quantity squared not equal to K over M. That's the first scenario I'm going to look at. So assume B over 2m squared is not equal to K over M. Okay. In that case, I'm going to realize that X, because I've got two different solutions, there's one associated with a plus sign and there's one associated with a minus sign. I've got X is going to be, instead of just A times e to the rho t, I'm going to have to call it A1 for one of the terms and A2 for the other term. So I'm going to say A1 E. Now I'm going to, well, I'll just go ahead and write it out. Negative B over 2m, and I'll explain this in a second, plus square root all that times t. Okay, so I'm using some shortened terminology here. I did write out the negative b over 2m in the plus part, but I just put a square root to represent that. Now the other one's going to be plus a2, some other constant. And remember, second order equation should have two constants plus that omega thing we suspect is going to come out. So in this case, I get negative b over 2m minus the square root, all that times t. Now, you should recall that when you have two exponents adding in a given number, you could make one of them e to the negative b over 2m times t, and then the make that times e to the positive square root times t. In other words, it's sort of the opposite of the logarithm rule. The logarithm rule says that the log of a product is equal to the sum of the logs. Well, this is the reverse of that. The sum of exponents is equal to the product of the bases raised to each exponent. So I can write this further as x is equal to e to the negative b over 2m t, because notice this one has a negative b over 2mt and this one has it. So I'm going to pull out in front of everything, and then I'm going to say a1 times e to the square root t plus a2 times e to the negative square root t. Again, that square root is just all this junk in there. I just don't want to write it. So this is our solution, assuming that b over 2m squared is not equal to 4km. So as long as we have this as the case, then I have these solutions. But that's not the only story, because this b over 2m squared can be bigger than k over m, in which case this is just a normal number. But if k over m is bigger than b squared over 4m squared, then we get an imaginary number. So I've got to not only break it up again, because I've already broke it up once in terms of not being equal. Now I got to break it up for the case where this is larger, and then for the case where this is smaller. So, or vice versa. So I'm going to say first case, assume, and the reason why I'm doing this one first is because it actually gives you oscillatory equation. So I'm going to assume k over m is actually greater than b over 2m squared. Okay. And of course, when I do that, I can get very specific values and all that good stuff. But the main thing is that's going to make my square root become I times the negative of the square root. Right? Because when this under here is negative, then you can make that into the square root of -1 times the square root of this in reverse order. So that's all I'm going to do is put this in reverse order in there and put an I in front of it. So this is the first case. And in fact, I'm going to now say that x is equal to e to the negative b over 2mt times a1e. Now notice the first one's positive, so I'll say I times the square root k over m minus b over 2m squared times t plus a2 e to the negative I square root k over m minus b over 2m squared times t. And that's the function we have. The reason why I like this one is because of this I and this I, you actually get a sinusoidal term, because remember what I told you in the beginning of class, that e to the I theta is actually equal to cosine theta plus I sine theta. And I didn't tell you this part, but I think you can see it's obviously going to be the case, but e to the negative I theta is going to be cosine theta minus I sine theta. So what you get is this part right here is going to have a real part, cosine theta, and an imaginary part, negative I sine theta. And this one, the same thing, is going to have a real part, cosine theta, and an imaginary part, I sine theta. But we can just ignore the imaginary part because that's just imaginary, right? It's just like solving a quadratic equation, and you get the answers are negative 4 plus 2i and negative 4 minus 2i. You don't have to do anything special. You just say, well, it's obviously that, okay? So with that in mind, we could, for instance, if you want to choose very specific values to allow this to work out, you can do certain things, like you can say, let's say b is equal to 3, let's say m is equal to 3, and let's say k is equal to 2. And then we're going to also say that x of 0 is equal to a, which we're going to call 4 meters. And we can say v of 0 is going to equal 0 meters per second. And that's all our initial conditions we need. So with all of that, we can actually figure out all this stuff. And these particular b, m, and k values actually make it such that k over m is greater than b over 2m. So let's look, k over m, that would be 2 over 3. And b over 2m, that's 3 over 2 times 3. So that's 3 over 6. That's 1/2. 1/2 squared is 1/4. Clearly 1/4 is less than 2/3. So that actually works. Okay. So when I do that, let's go ahead and show you what actually works out. Looks like I got plenty of time. So what I'm going to have now is I'm going to say x is equal to, we already said b over 2m is going to be, do we say that's 2/3? That'd be, or that's 1/2, isn't it? B is 3, and then 2 times 3 is 6. That's 1/2. So this is e to the negative 1/2 t times a1 e to the I. And actually, let's go ahead and skip it. Let's don't say e to the I. Let's go ahead and plug in our cosine theta, because this is a positive I, our cosine theta, and just ignore the I sine theta, because we're completely allowed to do that, right? It's just an imaginary part. It doesn't even, it has no real meaning. So I'm just going to say a1 times cosine. And now I've got to do the reverse of this, which is going to be k over m. And of course, k over m we found was 2/3. So that'd be 2/3 minus b over 2m is going to be 1/2, and then we're going to square it. It'd be 1/4 times t. And then over here, I'll say plus a2 times, again, I'm going to go ahead and skip the e. I'm just going to go ahead and take e to the negative I theta is just cosine theta minus I sine theta, but the I sine theta is an imaginary part, so I'm just going to take cosine of theta again. So again, I'm going to get A2 cosine of, oh, and I forgot square root. That's the whole reason I wrote that out like that was, so cosine 2/3 minus 1/4 square root of all that junk times t, and I'm going to put a square bracket around that, and then a regular parenthesis around that. So that's actually my function. And in fact, we know that 2/3, if I multiply it by 4/4, I get 8/12. And if I multiply this by 3/3, I get 3/12. 8/12 minus 3/12 is just 5/12. So it's root 5/12, which you can shorten, of course. Let's see, this is going to be times 4, so this would be 8/12 minus times 3. This would be 3/12. That's going to be square root of 5/12. Whoa, a lot of bad just happened there. So just doing the arithmetic over here on the side so you can see what I'm talking about. We'll go to the next page and straighten it out. But this 15 was supposed to be a 12. And 12 is the same thing as 4 times 3. And of course, the square root of 4 is 2. So I can say that's 1/2 root 5/3. Like that. So that'll be a simplifier that we use. Now, what I'm going to do is pull this page off and continue on the next page, but I'm going to leave it where I can see the last page, or where you can see the last page, like that. So now we're taking that same expression. We're going to say x is equal to e to the negative 1/2 t times, I'm going to use a curly bracket, a1 times cosine. We just determined that that is 1/2 of root 5/3. So I'm going to say 1/2 root 5/3 t. So I'll put this there and a square bracket there. And then plus a2 times cosine of the same thing, which again would be square bracket, parenthesis, 1/2 root 5/3 t, parenthesis, square bracket, curly bracket. So that's our function. Okay, now that I've been able to copy that. Now I'm going to take my initial conditions, and my initial conditions were that x of 0 is equal to a, which is 4.00 meters, say. So we can actually keep it in terms of numbers. And obviously, you know, the b equaling 3 means b is equal to, notice it has to have units of newtons, Newton seconds per meter. So that's 3 Newton seconds per meter. And you could assume it to any number of decimal places. Of course, m being equal to 3 means 3.00 kilograms, and k being equal to 2 means 2.00 newtons per meter. So we have all those as real units. I just wanted to make sure you guys knew that. So that's one of our boundary conditions, our initial conditions. I'm going to call that one. The other one is that dx over dt evaluated at t equals 0 is actually equal to 0.00 meters per second. So I still got to take a derivative of this, but it's going to be a lot easier now. Okay. So this will be equation 2. So let me first calculate dx dt. Well, what I'll do is I'll first take the derivative of this and then multiply it by this. Well, the derivative of this is just negative 1/2 e to the negative 1/2 t. So I'm going to say negative 1/2 e to the negative 1/2 t times a1 cosine square bracket plus a2 cosine square bracket, like that. And now I've got to take and multiply this by, or add it first, but add it to e to the negative 1/2 t. And now I got to take the derivative of that junk. Well, that junk's actually not as bad as it seems. Derivative of cosine is just negative sine. And then I got to take the derivative of this. So I'm going to say this is negative 1/2 root 5/3 sine square bracket. And this other one's the same thing. Wasn't a negative though. I don't know why I said negative at all. So let's take that out. That's positive. Okay. And the same thing's going to happen. Oh, yeah, it was because the derivative of cosine is negative sine. So the same thing's going to happen over here. And I'm going to get, I'll put this and just call that A1. And then I'll do negative A2 times 1/2 root 5 over 3 times sine of the same square bracket thingamadigger. So that's it. So now I can say 2 implies when I plug in t equals 0, this just becomes, for starters, the left-hand side is 0.00 meters per second is equal to negative 1/2 times 1 times the cosine of 0, of course, is 1. So that's just A1 plus A2. And then plus, this would be a 1 again. Now a curly bracket. Sine of 0 is just going to be 0. So this is negative 0 minus 0. So lo and behold, I get that 0.00 meters per second is equal to negative 1/2 A1 minus 1/2 A2. So that's going to be like our 2' condition. Now I can do this one. That's going to be a lot easier. So 1 is going to imply that 0, or excuse me, that 4.00 meters is equal to, I take that, I raise it to the 0 power. That's going to be just 1. Curly bracket, A cosine of 0 is just A1. And then A2 times the cosine of 0 is just 1 again. So I get that. So I see that A1 plus A2 is equal to 4. And I also have that A1 equals A2 by this equation. Notice 0 is equal to negative 1/2, negative 1/2. So you can clearly get positive 1/2 equals negative 1/2. Excuse me, yeah, positive 1/2 A equals negative, maybe it's different by negative. Let me not take that step. So 1 over 2 A1 is equal to negative 1 over 2 A2. Oh, they're negative of each other. Yeah, that looks right. Okay. So I can combine these two and now say that A1 is negative A2. So I'll say negative A2 plus A2 is equal to 4. That's impossible. I don't know what happened there. Must have dropped the sign somewhere. This is negative. That's negative 0 though. This is negative A1 plus A1, negative 1/2 times A1 plus A1. Yeah, that works. Derivative of this, negative 1/2 times 0 times 1. So that's right. And then A1. And this is all A1. So yeah, that's A1, A2. And then this is 0 and 0. So that should be it. So I got negative. And this was a negative. Oh, hold on. Is that right with that A1 plus A2? Yeah, that should be A1 plus A2. So if I did this and divided it by negative 1/2 first, I'd still get 0 equals A1 plus A2, but that would still give me the negative. And that's a real problem. Because if I put in a negative here, whatever I substitute as negative is going to give me 0 is equal to 4. So that's not possible. Oh, I worked this out earlier, but I must have missed a term or something. What did I do earlier? I got 0 equals negative A1. Cosine, cosine, got that. And I got A is equal to A1 plus A2. So A is equal to A1 plus A2. I got that right. This is exactly what I did earlier. In other words, that's why I'm saying it's right. 657, crap. Then the derivative part where I had the velocity equal to 0 meters per second and t equals 0. That looks like the same thing I had before. Let's double check. I got A1 to the net times negative 1/2. Cosine, cosine. Oh, I know. No, I don't know. Oh, I'd made A2 equal to 0 beforehand. That's what had happened. Yeah, so there's some problem with this. Either way, the main thing that you should get out of this, you can actually conclude what I know is ultimately going to be the answer, is that A1 is equal to A2 is equal to 2.00 meters. And then you could say X is just equal to e to the negative 1/2 t times 4.00 meters times cosine of 1/2 square root 5/3 t. And that's the whole function, which really that 4 should be out in front, but that's actually the whole function. And what you see is basically a cosine function that looks like its height's 4. And since it has no phase angle, it's really going to start like this and do this. But the amplitude of 4 is being multiplied by e to the negative t. So it's actually going to cause it to shrink like this, which I've seen is one line. So in our actuality, what we get is a cosine function that goes like this. And that's called the underdamped version. Okay. Now, as you can tell, when we do the other part, when I do this being b squared or b over 2m squared greater than k over m, then I don't get a sinusoidal term at all. So I end up just getting 2 exponential decays, and that's the overdamped. So when we take b over 2m squared being greater than k over m, that's going to lead to overdamped. And it literally is a sum e to the negative t plus e to the negative at. In other words, it's going to be like 2 different a's. So it's going to quickly fall like that. And then when we do the b over 2m squared is equal to k over m, which I'll finish this next time since we're running out of time. When I do that case, that's going to be called critically damped. But the weird thing with that is you actually have to take the function, and since the b squared over b over 2m squared equals km, you don't get 2 solutions now. You get e to the negative b over 2m. That's just one solution. And the way you have to handle that is you now say x is equal to some a1 plus a2t times e to the negative b over 2mt. And that's the critically damped one. So notice this is linear followed by an exponential decay. This is a sum of exponential decays. And then this one was the one that actually looks oscillatory. So this is more like the door going into the kitchen of a restaurant that the waitresses go in and out of. It swings back and forth in time. Both of these just die out quickly. So they're underdamped, overdamped, and critically damped. I'll finish up this. I'll do the first case, working out more detail so I can show you exactly what happened with the boundary conditions and work out whatever problem is next time. But we've essentially finished chapter chapter 14. I'm going to spend a little bit of time, like I said, next time clarifying that, or I might just put it on my YouTube channel. But either way, we're finished with 14. And you folks are free to go. Stick around if you have any questions, or I will see you next time. Well,
I just have a quick question about the Mastering Physics due dates.
okay.
Were we supposed to do chapter 11, like the homework and the conceptual both for yesterday?
Yes, that was the due date. Of course, you have a little extension, but remember we finished 11 some time ago, and that's why I left those dates where they were. And 36 we finished before that. But like I said, you can do it a little late. You just lose a few points.
Yeah, I just wanted to check. Thank you.
No problem. Thank you, Rebecca. Anybody else?
Have a good night.
You too, Mario.
I had a question.
Yeah, Jared, go ahead.
On test 4.
Okay.
It's about the area under the curve on a force versus time graph. It's one of the conceptual ones. I know the answer is either potential energy or either kinetic energy, and I got it wrong, so I know it's the other one. But
actually, I don't think it's that either. It should be the impulse, which is your change in momentum.
Oh, because force versus time, not force versus distance.
Yes, force versus
distance
work, which is energy, and could be construed to be kinetic energy. But yeah, with this one, it's F dt is equal to the integral of dp, where p is momentum.
Yeah, I see. Okay, I think I was getting confused between the two integrals.
Yeah, that often happens because you're seeing so much stuff at once.
Yeah, you get kind of confused versus time and distance. Just one little letter.
Yeah, just one little letter makes all the difference in the world.
Yeah. Okay. I got it.
See you, Jared.
All right.